Hello, class 11th physics, chapter thermal properties of matter, topic calorimetry. Calorimetry means measurement of heat. So here we are going to study temperature changes, heat flow and causes of them, factors affecting them. So here we have few parameters and later on we'll uh, cover this principle of mixture. So let's start with heat capacity. So formula for heat capacity is delta Q by delta T. So what is it all about? Actually, it is the heat required to increase the temperature of a body. That's all. So we know that if we supply heat, temperature increases. But for different materials, different bodies actually, this heat capacity concept deals with the different bodies only. Not it is not related to their mass, their um, uh, constituents, or any other nature. There is a body, we have to heat it and we have to note down its temperature and we have to see that how much greater amount of heat or less amount of heat it requires. That's all. Okay, so the definition is heat required to actually amount of heat required to raise the temperature of a body by 1 degree Celsius or by 1 Kelvin. That is unit temperature. So we have just made a standard that through unit temperature, if it's how much heat is required for unit temperature change, how much heat is required. So its SI unit is joule per Kelvin, and it's a traditional unit. Those are CGS unit, not erg, calorie actually, calorie per degree Celsius. This is most commonly used with Celsius. It can be with Kelvin also, no problem with that. And also there is a bigger unit which is kilocalorie per degree Celsius. Next is specific heat capacity. It is the specific term. It is more inclined to the material. It is the property of material, not a body to body variation. So for an example, heat capacity for let us suppose there is an iron nail and an iron block and um, an iron ship, then all of them will have different heat capacity, because an iron nail, we will heat it, its temperature will increase immediately, so it has less heat capacity. A block, it will have more heat capacity, and a ship, if we heat it and we see change in its temperature through 1 degree or 1 Kelvin, we will see that still it requires large amount of heat. So although the three cases I have just discussed once again, so if I say that specific heat capacity of an iron nail, then uh, I have to say not the specific heat capacity of iron nail but the material iron. So iron is there in that nail, iron is there in that block, iron is there in that ship. So at that time, I would not say that specific heat capacity of iron of the ship. No, just the iron. All right, so its formula is C equal to delta Q upon M delta T. So once again, amount of heat required to off raise raise the temperature of unit mass of body by 1 degree Celsius or 1 Kelvin is called, why I'm writing this here, I didn't wrote that because it was heat capacity, but here is called specific heat capacity of material of the body. So its unit joule per kg Kelvin, and CGS unit, traditional CGS unit, otherwise it will be erg, but no, instead of erg we use calorie, so it will be calorie per gram per degree Celsius, most commonly. In fact, also in some books they consider kilocalorie and per gram, sometimes calorie per kg. So there are several combinations like these. I'm not including all those combinations here. These can be replaced by Kelvin also. So I'm not including all of them. You can understand that okay, it is made up of heat energy, that is by joule, mass, that is by kg, delta T, that is by Kelvin. Next thing, molar specific heat capacity. So it is related to some mole concept and all that. So C mu is equal to delta Q upon mu delta T. Mu, number of moles. So amount of heat required to raise the temperature of unit mole. So now we have introduced mole concept here. So per unit mole, mostly used for gases, so but can be used for any material. Unit mole of the body by 1 degree Celsius or 1 Kelvin is called molar specific heat. Molar specific heat capacity of the body, of the material of body. So its SI unit will be joule per mole Kelvin, or in CGS units it is calorie per mole Kelvin. Also it is kilocalorie per mole Kelvin. Well, if we talk about gases, then this is not only the requirement, that unit mass. There are several other aspects also. Like if we heat a solid or liquid, their expansion is also there. But in gases, that expansion is very, very large. So that is why uh, to raise the temperature of a gas, we have two methods. One at constant pressure, at P constant, then the specific heat, molar specific heat capacity, or simply specific heat capacity also we can call, we put Cp, and at volume constant it will be written as Cv. So we will discuss about it in later sections separately, not here. I'm just indicating you that this thing will also come. What is latent heat then? Okay, so latent heat is actually related to only when change of state takes place, change of phase take place, that is during melting or freezing, boiling. So actually if we uh, draw a graph between heat given and temperature of a body, let us suppose water, then let us suppose earlier it was here negative temperature. I'm marking it at in Celsius scale. So first it will rise like this, not so steeply linear. It can be bit it can be deviate from this linear portion, but somewhat approximately it will look like this. Then at 0 degree, if we supply heat, its temperature doesn't change. Here it is ice, till here it is ice, in between it is ice and water, and finally it becomes water. Later if we further heat it up, then its temperature raises, but when it reaches that boiling point, then it start boiling, and again its temperature stops increasing here. And when entire, okay, here it is water, here it is water plus vapor, and here it is completely steam, gaseous phase, and then it will further change. So what is happening here? During change in state, heat is required but no change in temperature. So L equal to Q by M. Latent heat is the amount of heat required to change the state of a body per unit mass, or we can say to change amount of heat required to change the state of unit mass is called latent heat. So we have latent heat of melting, that is fusion, and latent heat of vaporization. So in both these conditions, for fusion and vaporization, temperature remains same. We require some heat to change the state. That is called latent heat. For unit mass, So from here we can say its SI unit is joule per kg, and CGS unit, once again not erg but calorie per gram, calorie per kg, sometimes kilocalorie per gram, kilocalorie per kg. In fact, sometimes joule per gram is also used, but that is not SI unit then. Okay, next. Okay, so in this entire scenario, few things are there, like this latent heat during melting. Actually, what happens? Heat is required, so heat is absorbed. That is why in the hilly regions where fall takes place. So when that snow melts, people say it is much colder. Not at that time when snowfall takes place, but when it start melting, then they feel much colder, because at that time that snow absorbs heat from the surroundings, and that's why temperature of the surrounding falls, but not of the ice. Its temperature doesn't rise. It melt at 0 degree Celsius because of change in phase. Last topic, principle of mixture. So this principle is based upon conservation of energy. Based upon conservation of energy. Second thing, we assume that no heat loss is taking place. So if there is no heat loss between two systems, then, and we mix them together so that their heat can be exchanged, then okay, but before that, let us suppose m1, c1 small c, and t1. This is the mass of first object, mass of first, specific heat capacity of first, temperature of first object, initial temperature of first object. Similarly, we have another object, m2 mass. To save the space, I'm just writing m2c2 t2, and with t2 greater than t1. So if both are mixed, let us suppose common temperature. If we mix them together, then hot body get colder and cold body get hotter. So common temperature is T. Then heat lost by 2 is equal to heat gained by 1. It means M2 C2 and change in temperature, high minus low, T2 minus T, the common temperature is T now, is equal to heat gained by other object, M1 C1, and its temperature is increased now. So finally it reached T minus T1. So this is the principle of mixture. From here we can find T also, we can do further calculation here. Let me tell you again this entire thing which I have shown here. Let us suppose we have a half cup of hot tea and half cup of cold tea. Its temperature is T2, its temperature is T1, and we mixed them together, and then their temperature become T. Then you can say that it has lost its heat, it has gained its heat. So here temperature change will be T2 minus T, and here temperature change will be T minus T1. This is what I have mentioned here. So there are many numerical based upon these and principle of mixture. Then calorimeter, there is a device calorimeter. So I will discuss about those worked out problems, some application based question, and working of calorimeter in next video. Bye.